In this class, we are going to discuss some of the techniques that is widely used for developing nanostructures. A variety of methods are available to develop nanostructures with controlled shape, size, dimensionality, and structure. Each of those methods has their own merits and demerits. The key issue with any type of fabrication technique is the size controllability, as the quantum confinement effects strongly depends the size of the nanomaterials or nanostructures. We will be discussing only a selected few methods that is used for fabricating nanostructures for photonic applications. There are two general approaches to the synthesis of nanomaterials and the fabrication of nanostructures: top-down and bottom-up approaches. Top-down approach involves the breaking down of the bulk material into nano-sized structures or particles. Top-down approaches are inherently simpler and depend either on the removal or division of bulk material or on miniaturization of bulk fabrication process to produce the desired structure with appropriate properties. Some of the examples are various lithographic techniques like ultraviolet, electron beam, X-ray, focused ion beam lithography, etc., and various milling processes. Top-down refers to the traditional workshop or microfabrication method, where the tools are used to cut, mill, and shape material into the desired shape and order. The biggest problem with the top-down approach is the imperfection of surface structure. For example, the nanowires made by lithography are not smooth and may contain a lot of impurities and structural defects on its surface. Bottom-up approach refers to the buildup of a material from the bottom, that is atom by atom or molecule by molecule. Such atom by atom or molecule by molecule deposition leads to the formation of self-assembly of atoms or molecules and clusters. These clusters come together to form self-assembled monolayers on surface of the substrate. In all the bottom-up techniques, the starting material is either gaseous state or liquid state of the matter. Various physical vapor deposition techniques like evaporation, sputtering, laser ablation, and chemical vapor deposition techniques like CVD, MOCVD, PECVD, etc. are the examples of bottom-up approach. First technique that we are going to discuss is the molecular beam epitaxy, or popularly called MBE. The word epitaxy comes from the Greek words epi means above and taxis means the deposition in ordered manner. So epitaxy is a method of depositing a monocrystalline film on a monocrystalline substrate. The deposited film is called the epitaxial film or the epitaxial layer. Epitaxial films can be grown from gaseous or liquid precursors. Substrate here act as a seed crystal, where the crystalline lattice of the substrate provides the template for the growing layer to orient itself. Lattice matching between the substrate and the growing nanostructures plays an important role in the fabricated nanostructure. Molecular beam epitaxy is a widely used method for epitaxial growth of quantum confined structures. A molecular beam epitaxy machine is essentially an ultra high precision, ultra clean evaporator combined with a set of in situ tools such as Auger electron spectroscopy and or reflection high energy electron diffraction read for characterization of the deposited layers during the growth process. And this is how it looks like, and this one shows a simplified schematic representation. In solid source MBE, precursors are in elemental form. Ultra pure elements such as gallium, indium, arsenic, tin, etc. are heated in a separate effusion cell until they begin to slowly evaporate. An effusion cell is typically a crucible with a heating element and an orifice and a shutter. The vapor formed by heating of the cells passes through a small orifice and accelerated by the pressure difference on the two sides of the orifice. It forms a molecular beam within which the particles neither interact nor collide with one another. The evaporated elements then condense on the substrate where they may react with each other. If we are evaporating gallium and arsenic, a single crystal gallium arsenide is formed on the substrate, which is placed opposite to these evaporating sources. Term B means that evaporated atoms do not interact with each other or any other vacuum chamber gases until they reach the substrate due to the long mean free paths of the beams. The substrate is rotated to ensure even growth over its surface. By operating mechanical shutters in front of the cells, it is possible to control the semiconductor or metal which is being deposited. For example, opening the gallium and arsenic cell shutters results in the growth of gallium arsenide. Opening indium cell now results in the growth of indium gallium arsenide. Position of the resulting film can easily be controlled by controlling the temperature of the effusion cell. As the shutters can be switched rapidly in comparison to the rate at which material is deposited, it is possible to grow very thin layers exhibiting very sharp interfaces as shown in this cross-sectional TEM. You can see here very precise layer by layer growth of indium gallium arsenide and gallium arsenide layers on top of a single crystalline n-type indium phosphate substrate. Typical deposition rate is very slow and can be controlled of the order of 1 nanometer per minute. This helps us to have a fine control over the thickness of the layer grown on the substrate. Hence, the MBE method is well suited for fabrication of quantum wells. An animation of the growth dynamics is uploaded in the Moodle, which you can watch to know how evaporated atoms are actually getting deposited on the substrate. This slide is to give you an idea what we mean by molecular beams. Different gas flow patterns are typically observed when a vacuum system is evacuated by a pump. As the pressure the system decreases from atmosphere to very low pressures, gas flow patterns changes from viscous flow to molecular flow. In viscous flow, gas flow is limited by the viscosity. Distance between the molecules is very small and hence molecule-molecule collision happens very often. And then the flow happens through the momentum transfer in the collisions, and this regime exists generally for pressure greater than 0.1 millibar. In molecular flow, particles move freely without mutual hindrance. Flow is limited by molecular phenomena. The distance between the molecule is very large and hence the collision between the molecule is absent. Molecule wall collision dominates. The flow occurs through random motion, and this regime exists generally for pressure less than 10 raised to minus 3 millibar. In molecular beam epitaxy, evaporated beams of elements are maintained in the molecular flow regime by controlling the rate of evaporation in an ultra high vacuum system. Another well-known method for quantum structure fabrication is metal organic chemical vapor deposition, which is popularly known as MOCVD. MOCVD is a chemical vapor deposition method in which the precursors for the elemental constituents of the semiconductor structure to be grown are in metal organic chemical form. Hence, the precursors used here are different from the ones used in the case of MBE, in which case the precursors are in the elemental form. Metal organics are a class of compounds consisting of metal ions or clusters coordinated to organic ligands. When the MOCVD method is used for the epitaxial growth on a substrate, It is also called metal organic vapor phase epitaxy or MOVPE. The mechanism of an MOCVD technique is very simple. MOCVD relies on the gas phase transfer of the material to be deposited on the substrate. The deposition ultimately occurs via a chemical reaction at the substrate surface and typically results in high quality epitaxial thin film deposition. Because MOCVD utilizes heated gas flow and surface chemical reaction, the substrate temperature for typical device growth are higher than MBE and in 500 to 1500 degrees Celsius range. One of the advantages of MOCVD method is that it is a simple growth technique with a growth rate typically 10 times that of MPE. Another advantage is that no vacuum requirement is needed and hence maintenance becomes cheaper than that of MPE. However, one serious issue with this method is the use of extremely toxic precursors. It demands extreme safeguard and a care in handling. As it is a non-vacuum technique, in situ characterization tools cannot be used to monitor the nanostructure growth. Chemical beam epitaxy is a combination of MOCVD and MPE. It utilizes an ultra-high vacuum chamber like in MPE, but the constituent elements are derived from metal organic precursors as in MOCVD. The method thus offers the advantage of both MOCVD and MBE. Liquid phase epitaxy or LPE is a deposition method for getting high quality films from the liquid phase. A substrate is brought into contact with a saturated solution of the film material at an appropriate temperature. The growth of epitaxial layers occurs in two different types of LPE setups, one for the dipping process and the other one for the tipping process. Dipping refers to a process in which the substrate is dipped vertically in the melt. Tipping is a process where we use a graphite crucible which contains both the melt and the substrate. By tilting the crucible, the melt flows onto the substrate. The substrate is then cooled at a suitable rate to lead to a film growth. Advantages of LPE includes lower cost and higher deposition rate compared to those for MBE. LPE also provides a control of stoichiometry and yields low defect concentration. A disadvantage of LPE is that the solubility considerations greatly restrict the number of materials for which this method is applicable. Furthermore, the morphology control is difficult and surface quality is often poor. Chemical vapor deposition or CVD is a generic name for a group of processes that involve depositing a solid material from a gaseous phase and is similar in some respect to physical vapor deposition or PVD. Physical vapor deposition differs in that the precursors are usually solid. The material to be deposited being vaporized from a solid target and deposited onto the substrate. In a typical CVD process, the substrate is exposed to one or more volatile precursors which react and or decompose on the substrate surface to produce desired product. Frequently, the volatile byproducts are also produced, which are removed by gas flow through the reaction chamber. Precursor gases are delivered onto the reaction chamber at approximately ambient temperatures. As they pass over or come into contact with a heated substrate, they react or decompose, forming a solid phase which are deposited onto the substrate. The substrate temperature is critical and can influence what reaction will take place on the substrate. A CVD apparatus consists of several components like a gas delivery system for the supply of precursors to the reaction chamber, a reaction chamber within which the deposition takes place, a substrate loading mechanism for introducing and removing substrates, energy sources which provides the energy or heat that is required to get the precursors to react or decompose, a vacuum system for removal of all other gaseous species other than those required for the reaction or deposition. An exhaust system for removal of volatile byproducts from the reaction chamber. And then exhaust treatment systems. In some instances, the exhaust gases may not be suitable for release into the atmosphere and may require treatment or conversion to safe, harmless components. So, in such cases, we use an exhaust treatment system. And then the process control equipments like gauges, controls, etc., to monitor the process parameters such as pressure, temperature, and time. There are several suitable sources of heat for CVD process. These include resistive heating, for example, in tube furnaces, or radiant heating, like that in the case of halogen lamps, or radio frequency heating, as in the case of induction heating, and lasers can also be used for heating purpose. MOCVD that we discussed earlier is a special form of CVD. If we use a laser beam as a source for heating the substrate instead of resistive heating, we call it as laser induced chemical vapor deposition, or LCVD. The use of laser as the heat source chemical vapor deposition offers several distinct advantages like excellent spatial resolution, limited distortion of the substrate, possibility of cleaner films due to small area of heating, etc. Another example of laser assisted vapor deposition involves the laser decomposition of the precursor gaseous molecules to produce the desired materials. Laser assisted processes have also been used for depositing thin films and nanoparticles in physical vapor deposition schemes. For example, the ablation of a solid target is possible with lasers where the ablated materials are deposited onto a substrate. A laser beam is focused through an optical window of the vacuum system onto a solid target material. The laser beam then vaporizes the evaporant and subsequently deposits it on a substrate which is placed opposite to the target material. Deposited film usually maintains the target stoichiometry. Alternatively, the ablated material can be mixed with a reactive gas to make the appropriate material, then carried by an inert gas through a nozzle into a vacuum chamber to produce a molecular beam, and then deposited on a substrate whose temperature is controlled. And this method is also called a laser assisted molecular beam deposition.